All right, everybody. So today we're starting our discussion on work, energy, and power. All right. So in front of me, I have this question. So we have a truck mass of 1,200 kg, which is moving down a rough inclined track. And this truck has a speed of 0.8 meters at point P, where point P is 1.8 meters above the ground level QR. All right. So the length of this of QP is 2.2 meters, and when the track reaches point P, it has a speed of 4 meters above the ground. All right, I'm sorry, my screen disappeared, so I'm still trying to head it back. All right, it's back. Okay. So the truck at point P has an initial velocity of 0.8 meters per second, and point P is 1.8 meters above the ground level QR. All right. So at point P, the car will have, or the truck will have, maximum potential energy because it is 1.8 meters above the ground. But when it is at point Q, it will have minimum potential energy because it is at ground where the height is 0. Yeah, and we know that potential energy is the consequence of height. So if there is no height, therefore there will be no potential energy. Okay, now let's look at kinetic energy. So the velocity at point P is 0.4, but the velocity at Q is 4 meters per second. So at point Q, the truck will have a higher kinetic energy compared to point P because there is an increase in velocity, and we know that kinetic energy is the consequence of velocity. So if you increase the velocity, you're automatically increasing the kinetic energy of an object. All right. Then you are also given here the displacement which will be undergone by the truck QP, which is 2.2 centimeters. And another thing that we need to note here is the rough inclined track. So this rough inclined track will impose a friction in the car tires. Therefore, mechanical energy of the system will be not conserved because we know frictional force is a non-conservative force. So it will do negative work in the system, therefore decreasing the mechanical energy of the system. So the mechanical energy of the system or of this track will not be conserved. Okay, so before attempting to answer any question, so let's draw the free body diagram to identify all the forces that are acting on the track. So here we have an inclined surface, but we're not given this guy, this angle theta there. Then we have this track. Okay, let me draw. Okay, it's fine. Let me draw a free body diagram, not a force diagram. So we have this car. We have FG parallel. We have normal force. FG parallel. We have normal force. We have FG perpendicular. FG perpendicular, and we have a frictional force. All right, but we'll have a problem here because this guy over here, and no, this one should be perpendicular. I'm sorry. So this guy over here, FG perpendicular and FG parallel, depend on this guy over there, this angle, which is not given to us because by definition, Fg parallel is equal to mg sine theta, and Fg perpendicular is equal to mg cos theta. So now we won't be able to use a formula which will feature this guy over here because we don't know the value of cos theta. All right, so let's attempt the question and see. How are we going to tackle this problem? All right, so in 5.1.1, we need to state the principle of conservation of mechanical energy in words. All right, so mechanical energy is the sum of kinetic energy and potential energy. And this principle now states that the total mechanical energy of the system is conserved, or rather it remains constant if and only if there are no external forces, or if our system is an isolated system. So in simple terms, in an isolated system, the total mechanical energy of the system remains constant. So I'm not going to type that out. So let's try to answer to 5.1.2. All right. So is mechanical energy conserved as the track moves from point P to point Q? Choose yes or no. No, it is not conserved. So mechanical energy is not conserved because some energy will be lost in the form of heat or sound due to friction in the tires. So, and friction, we know it's a non-conservative force, so it will decrease the mechanical energy of the system. So mechanical energy is not conserved. All right. So 5.1.3. Use energy principles to calculate the frictional force acting on the track as it moves from point P to point Q. So we can try to use this guy, the work energy theorem. So now we have identified the forces that are acting on this on the track, and we said it's this guy because our motion is on this direction. So we're going to choose the forces, this force and this force, which are on this direction. All right. But the problem is that Fg, we can't use Fg parallel because we don't know the value of theta. All right. So that means now this formula over here fails. So we need to try other formula. So let's try this one and see. Work done by non-conservative force, because we have a non-conservative force there. So it should be equal to change in kinetic energy plus change in potential energy. And now we have the initial velocity and final velocity, so we can compute this guy over there. And we also have initial height and final height, so we can compute this guy over here. So what I'm going to do, I'm just going to compute change in kinetic energy separately and change in potential energy separately. Then I'm going to add those two, or rather substitute in this equation over there. All right. So what is change in kinetic energy? It's half mv squared final minus half mv squared initially. All right. So change in kinetic energy is equal to the half, our mass is 1,200, then our final velocity is 4 squared, minus half of 1,200, then our initial velocity was 0.8 squared. So this change in kinetic energy will be, 0.5 times 1,200 times 4 squared minus 0.5 times 1,200 times 0.8 squared. So it's going to be 9,216 joules. Okay, that's the change in kinetic energy. Then the change in potential energy will be mgh final minus mgh initially. All right. So our mass is it's 1200 times 9.8 gravitational constant. The final velocity is 0. Then our mass is 1200, then 9.8. Then our initial height was 1.8. So 1.8. So the change in potential energy now will be equal to 0 minus 1200 times 9.8 times 1.8. All right, which will be equal to minus 21,168 joules. So that is the change in potential energy. So now substituting back to the original equation. Okay, so change in kinetic energy plus change in potential energy. So we said the change in kinetic energy is that 9,216, 9,216. Then the change in potential energy is 21,168. So this is the work done by non-conservative forces, which is equal to 9,216 minus 21,168, which is equal to minus 11,952 joules. So this is the work done by non-conservative force, which is negative because this non-conservative force is decreasing the energy of the system. But now we need to identify all the non-conservative forces which are acting in this system. And in this case, we said it is only the frictional force. So work done by non-conservative force now is equivalent to the work done by friction. All right. But according to the definition, work done by friction is equal to the frictional force itself times delta x, which is the displacement cos theta, where this cos theta determines if the force is doing negative work or positive work. All right. So in this case now, we know that the frictional force is doing negative work. So this theta over here will be 180 degrees. So if it was doing positive work, we're going to substitute by 0 degrees. So the displacement was given to be 2,2. So in the place of cos theta, I'm going to substitute by cos 180, which is equivalent to -1. All right, 952. So now we have FR times 2,2 times -1 is equal to minus 11,952. So 2,2 times -1, all right. So I'm just going to substitute by -2,2 because -1 times 2,2 is minus 2,2. Then also this side, I'm going to divide by -2,2. So frictional force now will be equal to this minus 11,952 over minus 2,2, which is equal to 5,432,73 newtons. So this is the frictional force we were required to calculate, and we have calculated it successfully. All right. So the next question now. So the driver of a 1,000 kg car traveling on a highway at 35 meters per second applies brakes to avoid hitting a van in front of him, which had to come to rest because of a traffic ahead. So, all right, I'm sorry. So we have a car which is traveling 35 meters per second. But now ahead of this car, there is another car which is at rest due to traffic. All right. So now the car at the back, which was traveling at 35 meters per second, had to stop because to avoid hitting the car ahead of it. So the driver had to apply now 8,000 newtons to stop this car. Okay, so let us identify all the forces that are acting in this car. So we have a normal force, we have a weight, then we have a frictional force due to brakes or the braking force, which is acting in the opposite direction of the motion. So so I'm just going to name this force frictional force or braking force. All right. So now in 5.2.1, we need to state work energy theorem in words. So I'm just going to state it mathematical, not in words. So you can take the definition from your notes or the theorem from your notes or from your textbook. So, but this principle states that the total work done in an object is equivalent to the change in the kinetic energy of that particular object. So that's the work energy theorem in words. All right, so now we need you to use energy principles to determine the minimum distance required for the brakes of the car to be applied to avoid a collision. All right, so if we want to avoid collision, in other words, how much the distance? So if we apply this 8,000 Newton force, so how much the truck or the car will travel before it hit the car ahead of it. All right. So the final velocity should be 0. Then initial velocity was given. So now we need to determine the displacement that will be undergone by the car just before it stopped and before it hit the car ahead of it. So the car should stop before it hit the one ahead of it. All right. So the only force that is acting here is the friction. So frictional force delta x cos theta. So this should be equal to change in kinetic energy, half v squared final minus half v squared initial. So we want this guy over here. So we're given the frictional force, and we know that frictional force is doing negative work, so it is decreasing the mechanical energy of the system. So this theta should be 180. All right. So the frictional force is 8,000. Delta x is our quantity of interest. Then cos of 180, because frictional force is doing negative work. So then half of 1,000. Then final velocity should be 0, because we want the cars to stop before it hit the one ahead of it. So I'm just going to substitute by 0 here to give myself some space. So for the final kinetic energy, then 1,000. Then initially the car was traveling at 35. So I'm going to have 35 squared over there. All right. So we have 8,000 times cos 180 degrees, which is -1. So we're going to have minus 8,000 delta x, which is equal to minus 0.5 times 1,000, which is 500, all right, times 35 squared. So we have minus 6,000, and no, 612, 500. So I'm going to divide by minus 8,000, both sides, minus 8,000. So our delta x will be equal to minus 612, 500 over minus 8,000. And therefore, the displacement is 76.56 meters. So if the driver is applying 8,000 brakes 8,000 Newton brake. Okay. So if the driver is applying brakes by supplying the brakes with 8,000 Newtons, so and the car stop. So this car is going to travel 76,56 meters. All right. So this is the displacement that is going to be taken or undergone by the car for it to stop just before it hit the one ahead of it. All right. So the next question is now we need to use energy principles to determine the speed at which the vehicle will collide if the driver had applied the brakes when his car was 30 meters behind the van. All right. So, okay. So now this question, the next question is related to the one that we just did. So I'm saying this car. All right. So we have those two cars. So this is the 1000 kg car. This is the one that is in front of it. So we're not told its mass. I'm just going to say M. So this one is traveling at 35 meters per second. So its speed is reduced because brakes are applied so that it stops just before it hit this one. So according to the calculation that we did, so this distance should be 76,56 meters. So it must stop around somewhere here before it hit this one. So this is the distance required. So it must be 76,56 meters away for it not to hit this one and ahead of it. All right. So the next question is now, if the car is 30 meters behind this one, so obviously it's going to hit it because it is very close. So the driver will need now to apply more brakes because remember the initial speed didn't change. So the initial speed is still 35 meters per second. So if he is still applying that 30 Newton force and the car is 30 meters, so obviously it's going to hit this one. So now we need the velocity in which it will collide with the one ahead of it. All right. So how do we answer this question now? All right. So we're going to use the same formula. But now what is needed here is the velocity. So now in this case we are given the displacement. So all right, so 5.2.3, 5.2.3. So work done by friction is equal to change in kinetic energy. So this work done by friction is the frictional force times the displacement cos theta, which will be equal to half v squared final minus half v squared initially. So the frictional force is 8,000. So the displacement is given now to be 30. Then cos theta is cos 180 degrees. Then the final velocity now will not be 0 because though the car will collide. So it's going to be half 1,000 times the velocity that we want minus half times 1,000. Then initial velocity was 35 squared. So half of 1,000 is 500. So I'm just going to substitute by 500 to give myself some space. So it's 500 initial squared, which is 35 squared. All right. So 800 times 30, or 8,000 times 30 times -1. So it's going to be minus 240,000 is equal to 500. VF squared minus 500 times 35 squared, which is minus 6,612,500. All right, so now we need to take this guy to this side. Then we're going to have minus 240,000 plus 612,500 is equal to 500 VF squared. And then minus 240,000 plus 6,112,500. So it's 372,500 is equal to 500 VF squared. Then we're going to divide by 500, divide by 500. So our final velocity, rather the square of it, it's 372,500 over 500. All right, which is 745. So if we take the square root both sides, so our final velocity will be equal to the square root 745, which is 27,29 meters per second. So the initial speed of the car was 35 seconds. So if this car is 30 meters behind the one ahead of it, so they will collide, and the car, the 1000 mass car will have 27,29 meters per second when they collide. So the last question, it's 5.2.4. So how would the speed calculated in 5.2.3 change if it was raining during the incident? Choose from increase, decrease, or remain the same, and give a reason. So now, if it was raining, so this speed over here, so it will increase. Because when it is raining, the surface tend to be smooth. So the water particles occupy the rough patches in the road. So the road now becomes smooth rather than being more rough. So therefore, when the surface is smooth, the friction is less. Therefore, the velocity will increase. Yeah. Thank you so much.